Okay. Controlling reaction rates and writing rate laws. Controlling is kind of a strong word. I mean, we can't control nature. We can just get good at predicting it. So we should have changed that to predicting. But it's important. I mean, just think if you're the Tums guys, right? I mean, making antacids. You want that stuff to react slowly, right? There's a lot of processes where you want to have an idea and I guess control's the word, but be able to predict really well how fast something's going to happen or how much you're going to get over a certain amount of time so you can remove that product. Kinetics is big on pretty much every process that they're making chemicals, and whether it's components of Pepsi or toothpaste. But we have two light sticks. Vanessa, can you see the ice here? Right? There's some ice here, and then we took the light stick out of the ice and then we put it in this hot water. How did the light stick change? What does it look like it changed? It got brighter in the hot stuff, right? Okay. So Albert, why would the light stick get brighter in the hot water? Yeah, definitely. Heat has a lot to do with it. Speeds up the reaction, right? And it's like light must be a product, so it speeds up the reaction, more light. Now the thing isn't going to last as long. If you bought one of those little glow-in-the-dark doohickeys, right? You go to the big celebration downtown, New Year's or whatever, and there's always guys running around selling the glow-in-the-dark necklaces and things, and you fork out $20 for it or whatever, and you want it to last as long as possible. Well, when you go home, where should you put it? In the freezer. Wow. Slow that reaction. It's still going to die on you, but at least you can slow it down a little bit. You can't see it in the freezer, so it's kind of a waste, but okay. Let's take a look at what's going on here. Some general ways to increase the rate of a reaction, to make it go faster. We can increase the concentration, Monica, of the reactants. Definitely. Okay. We could increase the Mari blank, especially when the reaction is blank. Increase the temperature. We know that with the light sticks. Especially when the reaction is blank. Endothermic? Why is Jessica right? Because heat is for endothermic, heat is a reactant or a product? For endothermic. Reactant. And that's what we said in the first one, right? Increase the concentration of the reactants. Things will go faster. So if heat's a reactant, dang, yeah, it'll go a lot faster. For endothermic reactions, things get, would that flask, if it was an endothermic reaction containing flask, would it get colder or hotter? Colder, right? Yeah, because heat's the reactant, sucking up all the heat from your hand and everything. We could also, Victoria, increase the blank of the reactants. Surface area. Here, a good example might be taking this piece of chalk, right, calcium carbonate, and maybe putting in a beaker of vinegar or something. I'll get some carbon dioxide bubbles going. But I could get a lot more carbon dioxide bubbles per second if I did what to this piece of chalk? I could put a bigger piece, but it wouldn't cut it into two, yeah, or increase its surface area. Yeah, smash it up. Make it a pulverize it, make it a powder. The last way that I can think of here, this is big money, this last one. If you can figure out how to develop one, use what? What would, man, I have two, oh, Eric. Catalyst. Use a catalyst. Catalyst is just something you add to a reaction, it speeds it up. It doesn't get consumed, it just stays there, but somehow it speeds up the reaction. So there's big money in developing catalysts. Okay, writing rate laws. What is a rate law? Well, the book says a rate law is an equation that relates the rate of a reaction to its concentrations of reactants raised to various powers. It's it sounds confusing, but this is the goal for today, to try to write rate laws, figure out what those powers are. Here's a general reaction. And Ramiro, if you're reading my general reaction right, what are the little numbers that you use to balance the reaction? That we're supposed to call them stoichiometric coefficients. What are they being represented by? Yeah, that's the question. Big one, the big letters or little letters? The little letters. The little letters are my numbers that you're changing. Little a, little b, and little c. Those are the coefficients. These are the numbers that, we change to balance the reaction. We're supposed to call them stoichiometric coefficients. Cassandra, how about what represents my reactants? Yeah. Well, which ones, though? Not all of them.
A and B.
Big A and big B. So the product is C. Exactly. Okay. So if this is a general reaction, then this is how you'd write the general rate law. All you do is write the word rate, and then equals, write a K. Now what the heck is the K, Summer? What is this? It's a constant. A blank constant. Probably a rate constant, rate law, so rate constant. Because if that rate constant K was not there, you'd have to replace the equal sign with a, what is that? Proportionality sign. So that's why it's in there. So you can write equals instead of proportional. But it's just a constant. Figure out what it is and it'll never change on you. Okay. Then you're supposed to write, so you write the word rate, and then the equal sign, then write the symbol K for rate constant, and then brackets A to the X power, B to the Y power. So it's the reactants, and you put them in brackets. What's the brackets part, Maria? What does this mean? I think we did this in 1401. Yeah. What does it represent? We did this when you wrote equilibrium constants. The what over the what? The concentrations of the products or the concentrations of the reactants. That's not what this is, but we wrote brackets. Remember that? We wrote the compound and we wrote it in brackets. So the brackets means concentrations, right? What were the units that we used a lot for concentration? We use big molarity, big M, right? That's concentration. Okay, and that's what the brackets means. And these X and Y, those are our powers, our exponents, whatever you like to call them. Now, Jasmine, are those little powers or exponents, are they going to be the little a and the little b? The little stoichiometric coefficients? Right? Now, if they are, if those powers, exponents, are the little stoichiometric coefficients, you know the numbers you have to change to balance it? This would be so easy. We can go home right now. Your homework would be a breeze this weekend. But it's not. Right? It's not even close. We have to figure them out. It's going to look, right? You got to figure them out. So they never are, so don't do it. I mean, I guess it's a chance it could be, but it's just by chance that it was like that. Okay, so our whole thing today is how to get these exponents X and Y. That's really what today's all about. Okay, so we'll do that. And once you do figure out what the X and Y are, if you just add them up, that's what the overall order is. So once you figure out what the rate law is, and you figure out what the little exponents are, add up the exponents, and that's what the overall order is. So I guess you could say X is the order of reactant A, Y is the order of reactant B. That would be the terminology. Overall order would be X plus Y. Okay. So from what you've seen so far, Brandy, does it look like products will ever show up in a rate law? No. Yeah, so don't ever do it. All right, don't ever do it. Okay, now before we get started, we're going to be setting up little relationships like this to find our X's and Y's. So I want to make sure we're all on the same page and know how to solve these algebraic relationships. So Jessica, on this first one, 4 equals 2 to the X. X equals 2. Right? 2 squared is 4. Good. How about Vanessa? The next one. Yeah, that X. That X has to be what? 2 raised to the what power will give you 2 again? 1. Anything raised to the 1 power just gives you itself. The next one here. Got no name. Someone's getting lucky today. It's probably AJ, right? I haven't picked on you this whole period yet, have I? Because I'm already back to Eric. AJ, what would X be? 3 times 3 is 9, times 3 is 27. Right, right? 3 raised to the 3rd. Last one, Albert. Yeah, anything raised to the 0 is 1. Well, somehow I skipped Eric. Anyway. X has to be 0. Okay. I still don't want to jump right into this. I want to show you the big picture here. So we'll run through this kind of quick, but they give you some general reaction. So the first thing I want you to do is write the general rate law. So you write rate equals K, and then you'd keep going. What would you write here, Alyssa? Brackets. Big E, right, to the X, and then keep going. Brackets, big F, exponent Y, right? That's the first thing I'd like you to do. And then you take a look at this table that they give you. Now notice the table has concentrations of each reactant. I don't know what that negative's doing there, right? Concentrations of the E and F. And then it gives you the rate of that reaction in that experiment. So they know what the concentration of E is, they know what the concentration of F is, and then they measured its rate. So it's just a table of a bunch of numbers. And the trick to doing this is to find two experiments where one of the reactants remains constant. So you pick 2 of them. Right? I don't know, maybe it's experiments 1 and 2 where E stayed exactly the same. They didn't change its concentration. Okay, so just pretend that's the case, right? That you compare experiments 1 and 2, and this number is the exact same as this number, so it's fine, it's constant. But the F, he went from, I don't know, 2 to 4 or something. He doubled. Okay, and the rate doubled. Well, how would I know the rate doubled? I'm actually going to have to divide one rate by the other one, right? Just see what happened. You're going to have to do that. You divide one rate by the other and see what happened to it. So the rate doubled. Then we're supposed to write an equation. Well, you follow it. You write it in the same format as this that we just wrote, our rate law. And we said that, and we just write in how things changed. So we said that the rate doubled. So we're going to put in a 2 for the rate. And then, does K change? Can K ever change? No. See, you can write a 1 in for it, but it just looks complicated. Just leave it alone, right? The K never changes. No, but the E, he didn't change either. So I guess you could put in a 1 for the K and be consistent here. E stayed constant, but you have to raise it to the X power. But it really doesn't matter because 1 raised to any power is always 1, right? 1 raised to the third, the second, the fourth, whatever. The -1 it's always 1. But f doubled. So you have to put in a 2 for how f changed, but that's raised to the y. So you see how this is starting to really look like one of these guys. So I really have 2 equals 2 to the y. So that means that my y is going to be in what in this case? 1. I just found one of the exponents. So if you pick 2 experiments where e's constant, f doubled, and you find the rate doubles, you're going to end up with one of the exponents being 1. Another option, what if you compared experiments 1 and 2 where e was kept constant, f doubled again, but now the rate quadrupled? Right? You divide this rate by this rate, and you got 4. So you write 4, right? The rate constant, and I'm substituting it into this order here. The rate quadrupled, rate constant, he didn't change. Concentration of E didn't change, right? But F, what did he do? He doubled, right? So I have to put a 2 to the Y. Now can you see what the equation is? 4 equals 2 to the Y. Y would have to be 2. Yes, Albert. Oh, K is a rate constant. So it doesn't matter what the experiment is, doesn't matter what the concentrations are or what the rate is, K is always the same number. K can never change. So when we're comparing, seeing how things change, K can never double or anything. It stays constant. So that's why I'm just putting in a 1 in for K all the time. Okay. And there's one last possibility here. The rate remains the same. So you compare these two numbers. It's the exact same rate. So what number would you put in for the rate? A 1. Yeah, it didn't change. Okay. A 1 in for the K. E didn't change. But now F doubles. So 2 to the Y. So what this is looking like, 1 has to be 2 to the Y. My Y would have to be 0. Okay. That's the big game plan. Let's see if we can get it to work. Now, before we jump in and actually do one, I want to play around with the terminology a little bit. Mari. Yes. Uh-huh. Good question. We're going to do that. Maybe you'll figure it out by the time we get there. Right? Keep it in the back of your mind. You hear a question? How are you going to find K? Should I just tell you right now?
Yeah.
All right, I'll just tell you right now. Okay. There's our rate equation, right? If we knew what the rate was, if we knew what the concentration of E was, if we knew what X was, if we knew what concentration F was, and if we knew what Y was, if we knew what all those things were, we could solve for K. Right? That's what you're going to do. You have to figure out everything. Figure out what X and Y are. Then all you do is pick an experiment. Any experiment, because any experiment tells you what the concentration of the reactants are, and it also tells you the rate. And the trick is it doesn't matter which experiment, because K is constant. So you can pick any experiment you want. And that's how you're going to solve for your K. Okay. And you ruined the surprise. Okay, oxalic acid is oxidized by permanganate to carbon dioxide and water. Here's our nice balanced reaction, right? And they said, here's the rate law. The rate law is, all the work is done. This is the rate law, except they didn't give us a K. I don't know why, but they didn't. Okay. Victoria, what is the order with respect to each reactant? What would you say? Can anybody help her out? Now the overall order will be 2. right? But the order with respect to each reactant is 1. And the reason why I did this is it's confusing. They never write the 1s, right? We should, though, because that's what our X and our Y are. They're both 1s. So with respect to each reactant, I guess you could say 1 and 1 or something, doesn't matter. But the overall order, 1 plus 1, would be 2. That makes sense? Okay, here's a real question. This is the homework. This is the quiz. This is going to be on the exam, definitely, for sure. Okay, yes? When they did the rate law, you know what it would look like? It would be concentration of H plus, but raised to the 0. Yep. So they left it out of there. It doesn't matter. All you need is some hydrogen. This concentration doesn't matter. It's not going to help speed things up or slow it down. So they found this for you. They did all the work. So you just use what they gave you. Right? Oh, I guess that's part of the answer. Each reactant, because hydrogen ion is a reactant. So you should say 0 for H plus. Right? Because look at that. Hydrogen ion is a reactant. That's true. Did you notice that? I don't know if the book would even have caught that. Okay. So here's our reaction. And there's a lot of English in here, but it's pretty much just the last sentence that matters. Get the rate law and get the rate constant. Okay? Get the rate law and get the rate constant. So let's start with Eric. Could you please give me your rate law that you would write? You know, the one where you write rate equals K. Well, there's no E or X here. You have to use this. Yeah, use the ClO2. ClO2 in brackets. Keep going. To the. If we take it to the second, there's no problem. Right? Yeah, don't do it. It might be a 2, but I doubt it. To the X, OH negative to the Y. That's where it starts. Write the general rate law. Okay. Now, Ramiro, see if you can pick 2 experiments where one of those reactants, its concentration stays the same. What 2 experiments could you pick? He says 2 and 3. He wants to compare 2 and 3. Yeah, look at that. ClO2 is staying at 0.02. Okay, let's see how this works. Let's compare 2 and 3. So if you compare those 2 rates, oh, Lauren, how did it change? Oh, we're going to need some solar energy here. Which one do you divide by which one? Yeah. Always the bigger by the smaller. Yep. In this case, the bottom one by the top one, right? So what did you get? Did you get 3? 3.1? What'd you get, Lauren? A lot of people got 3, though, so let's just trust them. Right? Rate change by 3. K doesn't change, right? The ClO2, you can just divide 0.02 by 0.02, and this always works, but it didn't change. Just 1 raised to the X. And then what are you going to put in for the hydroxide? Summer. What are you going to put in for the hydroxide? 3, yeah. Divide the 0.09 by the 0.03 and you'll get 3 to the Y. So 3 has to equal 3 to the Y. My Y has to be what, Maria? Has to be 1. Okay. We're close, Jasmine. We're real close. Okay, now we have to do it all again. Pick 2 other experiments now where the other guy remains constant. So not 2 and 3 anymore.
Experiment 1 and 2.
Yeah, 1 and 2. Because she sees this hydroxide staying constant. Right? Okay. Same idea. Rate equals K. Just so we don't screw up here. I don't think you need to write this again, but okay. How did the rate change? Brandy, how did the rate change? Compare those two. We're going to compare experiments 2 and 3. I don't know. What's 0.0248 divided by 0.00276? Is it 9? It's 8.9. Yeah, you have to round it up. It's going to be really close to a whole number every time. So you might have to do some rounding. So folks had to do some rounding to 9. Right? K never changes on you. ClO2. Jessica, what did that concentration change by? ClO2 changed by what? Divide the bigger by the smaller. Should be 3, right? The 3, right? 0.06 by 0.02, she's got 3 raised to the x. And you can divide the hydroxide changed by, well, divide 0.03 by 0.03. He didn't. So 1 raised to the y. And you can put in y if you want. Well, it is a 1, doesn't really matter. Right? So 9 has to equal 3 to the x. Man, Eric was right, wasn't he? X is going to be 2. Okay, so we're really close. We can write our rate law. Yes?
So I understood the whole concept, but where do you just drop the x after the whole thing, or then on the other problem you just drop the y? Or what happens?
Well, you can, because the reason why this simplifies to this is 1 raised to any power is always 1. Right? It doesn't matter what that y is. It doesn't matter. It's going to be 1. That's why we dropped it up here. 1 raised to the x. 1 raised to any power is always 1. That's why it disappeared on us. Good point. Good question. Okay. So now we can write our rate law. Our rate is equal to K ClO2 raised to the x, but the x is 2. Hydroxide raised to the y, but the y is 1. Now we have to get the K. Get K, and we're done. So Albert, the surprise was ruined, but do you remember how to do it? He wants to use experiment 2. Okay, what is he going to do with the data in experiment 2? Plug it in. Okay, he wants to use experiment 2. So let's use experiment 2's data. We know what the rate is. Put in the number for the rate. We know what the concentration of ClO2 is. Put in it. Raise it to the 2 power. Put in hydroxide's concentration. Raise it to the 1 power. And we'll be done. No, because K is the rate constant. It's the same constant for the entire experiment. It doesn't matter.
So what units would it
Let's figure out the units later. I'll show you. Let's get the number first. Okay, K. What is chlorine dioxide? Oh, we're doing experiment 2. So chlorine dioxide is 0.02 raised to the 2. Hydroxide is 0.03 raised to the 1. Okay. Now, if you know how to use your $5 jobby from Walmart, this is a pretty straightforward thing to do. You have to know how to use the calculator. Does anyone see how to do this? Does anyone know what I'm talking about? I'm talking about the x squared button. Right? You're going to take the point, what Eric was starting to get at, take the point 00276. So put that in there. Right? You got to divide it by both of these. So what I do is I hit the divide, 0.02, and hit x squared. Okay? So that's dividing by 0.02 x squared. And then divide it by 0.03, divide 0.03. And you get, what'd you get? 230. So you got to use these on the exam and stuff. What's that? Okay, the units. The units. That's going to be an ugly mess, but we could do it here. The rate has to be moles per second, has to equal K, and then you have big M squared, and you have big M. So my K units would be, I'm not really worried about units on the quizzes and things, but just for fun's sake, it would be big M all over, right, the squared and the M. You have the seconds down there. Boom, boom. My K is going to be 1 over M squared S. That'd be my units for K, if you want to use them. Yeah, it is. So I'll just stick with the 230 and be happy. Okay, you try this one. Okay. Find the rate law for this reaction. And I'll be glad to help you out. Jasmine, you have one of these? Okay, yeah, get used to using him. To get the right answer with that one, you have to start using parentheses and stuff. This one you don't have to worry about it. If you didn't quite get the last one, just let me know. Yep. Okay, 1.5, and then EXP Now it's asking for the power. The 2, and then there it is. That's it. Like 3 or 4 digits is good. All right. Oh, I see what you're saying. Which ones are you? Which 2 experiments are you? You're comparing experiments. This one and that one. Is that what you're doing, or which 2 are you doing? What 2 experiments are you comparing? Okay, you want to do these 2? And it has to be the bigger by the smaller. So you probably have to divide this one by that one, right? Because that's 10 to the negative 2. That's 10 to the negative 3. Yeah, C4. You'll get whole numbers on this stuff. If you divide the 2 rates, you get a number less than 1. You just divide it the wrong way around, right? So you're doing these 2? Yeah.
I got a Y for this one. I think I should have got X. These are the constants. These are not constant. And I solved for Y, I don't know why. So I should put 4 equals K 1 X and then 4 for 1.
Well, I think you need to write your general rate law. Otherwise, you might screw up NO and Cl2, right? Okay. So that's, yeah, so this guy, he's just going to be a 1 raised to the y if you compare these 2. Yeah, and then you get your x. Okay, what 2 experiments are you comparing? These 2? Okay, but if you compare these 2, everything is changing. Nothing ever stayed constant. So you don't want to compare 2 and 3. It'll be really ugly and a big mess. See that? Because none. Yeah, compare 3 and 1, and then the other one you can compare 1 and 2. Okay, yeah. See, 1 and 2 worked out. So hopefully you're comparing experiments 1 and 2, right? And then you're also comparing experiments 1 and 3. Those are the 2 that you got to compare. Otherwise, it's going to be an ugly mess. You have to get a K too on this. So see if you can get a K. Yeah, Romero?
The very last one is divider,
Yeah, you have to solve, pick an experiment, substitute it all into your rate law, and get a K. What'd you get for your K? It should be a huge number, I think. It can be a huge number. Rate constants can be, for very fast reactions, they can be really big. We'll see. 1 and 3. What did I do? 1 and 3, 1 and 2. Oh, did I screw up here? Oh, that's supposed to be a 3. Oh, I totally messed this up. Comparing 1 and 2. Yeah, it's 4. Okay. So you get rate equals K, NO to the 1, and Cl2 to the 2? Okay. What experiment did you pick to put it to find your K? The first one? Okay. Let's do the first one. We'll have, you should get a big number, 2.75 times 10 to the negative 3. K. NO is 1.2 times 10 to the negative 4. Cl2 is 4.8 times 10 to the negative 5. Has to be squared. So I'm going to take 2.75 times 10 to the negative 3, divide it by 1.2 times 10 to the negative 4, divide it by 4.8 times 10 to the negative 5. That has to be squared. And I get, man, why didn't I do it in scientific notation? I got to count all this stuff. It's like 9.9 times 10 to the, what'd you get? 2, 4, 6, 8, 9? Okay. So your entire rate law, your final answer, would be rate equals 9.9 times 10 to the 9. Oh yeah, otherwise you don't have your rate law done. NO to the 1, Cl2 to the 2. There's your final answer. Did you get that? I took up here 2.75 times 10 to the negative 3, right? And then divide by 1.2 exp negative 4, divide by 4.8 exp negative 5, push the x squared button, and then equals. You're plugging it in wrong. Show me how you're plugging stuff in. Yeah. Yeah. equals.
We're not pushing equals.
Yeah, we have to write in scientific notation though. Pretty dang close, 9.8. I just carried more digits or something than you.